This conference will now be recorded.
So let's start. So neural networks. They come originally from the brain. So we have about, sorry, here I think I have a mistake. It's probably some billion thing. It's probably in billion. So this is a biological neuron, what we have in the brain. So it has like 3 parts. It has the connections, B. We have a component here, C, and the output. And this is one neuron. So one neuron has multiple inputs, a cell inside that does something, and one output. It's exactly, if you can see, like a function, a multivariate function. It takes multiple inputs like this one, X, Y, Z, etc. And it produces something. This is one neuron. It's exactly like a function. Multiple inputs, one output. Also, like areas of the brain seem to have the same function, some areas in all humans. So for example, the motor area, the vision area, they are all the same for all of us. But other areas seem to be more plastic, and their function can vary from one person to another. The same area for me and you or any other person can do different things. And this, we suspect them to be like the areas that do the learning. They learn new things. So these neural networks, artificial neural networks, are algorithms that try to mimic the brain. They were very widely used in the 80s and early 90s, and then their popularity dropped, especially during the 90s. Like other algorithms were used, like the SVM, random forests, and other forest algorithms. And now they are the state of the art for many applications, especially vision, NLP, like they are unbeatable. And artificial neural networks that we are using right now are not nearly as complex yet as the brain structure. They are far less complex. This is an example of a feed-forward neural network, a layered feed-forward neural network. We have inputs, then hidden units, then outputs. We're going to see this in details, all of this in details. Let's first have a look at the perceptron. This is the simplest neural network that we can imagine. It's not even a network, it's just one single neuron. It was the first neural network learning algorithm in the 60s, and it is the simplest one possible. So this is the perceptron. So it has some inputs. It is like one single neuron, only one. It has multiple inputs. It can be any number of inputs, and it produces one output. It's exactly like the neuron that we have seen before. This is called the perceptron. Well, it's one single neuron, but the perceptron is actually the algorithm. So what does it do? What is this? We are here, guys, in the context. Let's take the context of classification. Classification means we have a data set like that. Here we have the input like height, weight, age, income, and you are trying to predict this, like something like education or whatever, or job, what is he doing, something like that. We are trying to predict something here. And it's not a number, it's just a class, what it is. This is the classification job. So how does the perceptron work? Sorry. Sorry, anyone ask a question? So let's see how the perceptron works. This is what is inside the perceptron, and these guys, x1, x2, xn, are coming from the dataset. These are coming from the dataset. This is one row of the dataset, one of the rows. We feed it to the perceptron. This is part of the perceptron. It does some computation, and it produces my result. This result is what we have here, what we want to predict. So what we do, it just multiplies the input by some weight, by this multiplied by this, and this multiplied by this. We sum them up. We sum them up, and we get a value. If this value is greater than a threshold here, a number, a threshold that we determine, then it's a class 1. We are here in this context, we are in a binary classification, 0 or 1, class 1 or class 2 or 0, 1. If it is smaller than this value, this threshold, sometimes it's 0.5, or it can be any number that we choose. Then it is 0. So what kind of function is this? Let's take, just to simplify things, let's take only one variable. We have only one variable. So this function will be x multiplied by y plus theta. We take it here, minus theta, sorry.
It's a line.
Greater or equal than 0. Yeah, it's just a linear function. It's just the function for a line. It's the same as ax plus b. It's the same. So this is what the perceptron is doing, something very simple. It's taking an input, if we are in two dimension, just to simplify, or where we are in one dimension, we have one thing. It's taking an input from here and compute something linear. For example, if this perceptron represents this line, we take this value, if we want to compute its prediction, and we compute something linear, which can be this value. For example, if this one is 1, this can be like 2 or whatever. So this is what the perceptron is doing, a linear combination. Multiply each variable by a weight, by a coefficient. Get the value. If the value is greater than some threshold, it's class 1. If not, it's class 0. So this is simply something like this, a linear function. This sum is just a linear function. Any questions so far, guys?
Yes, Reda, please. How we can represent the white here?
The W1.
Yes.
What do you mean? How they are just numbers?
No, how we can setting? I mean, in the setting.
This is coming. This is coming in the next slides. Today's session is basically how we can determine these W's. This is the main thing for today.
Reda, so can you please repeat what you said about getting the output value of Z? You either get 1 or 0. So what is the condition for 1 or 0?
So it's just we have this linear function. If this value is greater than a threshold that we set, then it is 1. If it's smaller, it is a 0. That's all.
Okay, so if the value is greater than theta, whatever value we get, if it's greater than theta, then it's 1. If it's not, then it's 0.
Yeah, that's all.
Okay, great. Thank you.
No problem. No other question. What I want you to remember is that this is all simply computing a linear function, which is one of the simplest functions you can imagine. So a perceptron is just a linear function. something that is like this, but in n dimension. Not here when we represent, it's just 2 dimension or 1 dimension, but it's just a linear function in n dimensions. This is the perceptron. And in that case, when we have a data set like this, a 2-dimensional data set, we have only here 2 features. Yes or no, guys? We have 2 features, and we want to know how to classify them accurately. So what the perceptron is going to do is to find a line that separates the 2. It's exactly like what we did in with the linear SVM, or what we did before with logistic regression. It tries to find a separated hyperplane, just a line. This is the goal of the perceptron. And this function that is represented here, or the W's, they are represented by the weights or the coefficients, are what represent this function, this line. Actually, it's perpendicular to it, but don't worry about this. These W's reflect this line. So if the perceptron determined this line, would it be good or bad?
Bad.
Not good, yeah.
Right.
Not too bad. Well, we have few errors. These are errors, and this is an error. This is better. If the perceptron found this line, the perceptron algorithm, then it is better. And the goal of the algorithm is to find the best set of W's, the best set of weights. Do you agree with me so far?
Yes.
Great. This is the algorithm of the first perceptron. I'm not going to dive deep in it because it's no longer used that much. We are not using other things. So I'm putting it here just as a reference. Let's go forward. So we put this notation, fx, it's what the perceptron has learned, w's multiplied by x, which are the variables, plus b. B is the residual, which is this one. Something like a theta or something. So this is a linear function. It's just an matrix representation. Don't be intimidated by this representation. It's just the sum of w's multiplied by all the x's plus a beta, which is exactly what a linear combination is. X, w, or a multiplied by x plus b, when we have only one variable. This is just to say we have multiple variables and multiple weights. So before we said that if this is greater than 0, because we have a b here. If it is greater than 0, then it is class 1. If it's smaller than 0, then it is class 0, or vice versa. Doesn't matter. We can use this function. Is this, just to remember your mathematical foundations, is this function continuous or not? Is this continuous or not?
Yes.
It's not. No, it's not continuous. It is 1 at some point, and then it jumps to 0. It's not a continuous function.
Yes. I thought x plus b.
Oh, no, yeah, x plus b is continuous, but this entire function is not continuous. This is continuous, but the output is not continuous. It's good to have something continuous. So what we do, we use the sigmoid function. The sigmoid function is something like that. It's almost 0 from here and 1 here. Almost, but continuous in between. I will tell you why we use something, we prefer something that is continuous. So this one is almost like 0 or 1. It's almost like this. But this one is not continuous because here we have a breaking point. This one is continuous. So this is the sigmoid function. And if we put f inside in here, in z, it's like we did the same thing. It's like it's almost equivalent to this. Do you agree with me? It's almost equivalent to this. So we put f inside, and we end up with something equivalent to this, but continuous. For those of you who attended the first part of the training, but does it remind you of something? Does it remind you of something we did before? What kind of function looked like that? What kind of classifier we used before that looked gritty like this one?
Not the convex, no?
Well, no, convexity is another concept. It's about the loss function. But what classifier we used that had similar representation like this one? Sigmoid of a linear
SVM رضا.
Not really.
Kernel, no?
It is logistic regression. Logistic regression was exactly the same as this. The sigmoid of a linear function. This is a linear function right here. Logistic regression was exactly like this, the formula for it. So a perceptron is very similar to logistic regression. One neuron is very similar to it. But it might be different if we use a different loss function that we are going to see later. The perceptron, guys, can find a plane or a line that divides my data. But if the data is not linearly separable, it cannot find a solution. The perceptron is not able to find a solution in that case. Okay?
Yes.
Do you agree, guys? Please,
Yes.
if you have any question or if you are struggling, stop me, because we are going to add more information, more concepts, and you may get lost. So please stop me and ask questions. Okay?
Yeah.
So a perceptron just find the line that divides my space. We have multiple lines that can divide the space. You can have this one. You can have this one. The original perceptron will find any one of them, which was not necessarily the best way of doing things. But it finds a line if it exists. If it exists, it will always find it. So the goal now, we find the best set of W's that minimizes an error. The error is related to the perceptron predictions on the dataset. We call the function to optimize a loss function. I'm going to explain this. So how can we find these W's? The goal is to find these W's to be able to find this line. The goal is to find this set of W's so we can find a separated hyperplane, this line, that can separate the red from the blue. Can you, just with the data set, find the best W's without doing anything? Do you know how this should look like?
No.
Do we know how this should? Sorry?
With dataset, we have X as input.
Yeah, we have the inputs and the outputs from the dataset. Now here the X's, the inputs, and here we have the output. So how should this look like? How can we find the best set of W's to find this hyperplane? How this W should look like? In its own, like this, we can't do much. We don't know how it should look like, what values of the W's we should take in its own. We need something that we can measure if it is good or bad. We need something that we can measure to say if it is good or bad. This is why we use the loss function. The loss function that we are going to see later in more details. Just tell us if a set of parameters, W's, are doing a good job or a bad job. That's the goal of the loss function. Does our W's do a good job or a bad job? And we have a number of loss functions. We have the hinge loss. This comes from the SVM. It's also used with the perceptron. We have the 1-0 loss. It's one of the old losses that we are not using much now today. This loss just counts the number of bad predictions that we made and sum them up. So if we, for example, if our perceptron values, these W's represent this vector, how many errors do we have?
Two.
How many errors?
Two.
Two errors.
Yeah, so the 1-0 loss is going to say 2. This is not a very good loss function. I will explain why. The 1-0. We have the cross entropy, the very famous cross entropy. It's used with the logistic regression and used a lot in deep learning. We have the mean square error and the mean absolute error. These are used for regression. These are more used for regression. These are used for classification. These are used for regression. Do you still know what is the difference between regression and classification? Do you want me to explain it?
Yeah, regression for numbers.
Predicted
digital,
numbers, yeah, continuous
digital,
numbers.
Yeah.
Yeah, classification is to classify in
Label or
labeling something. Are you all happy with this, guys? Do you want me to explain it or you are fine with it?
Okay.
Perfect. So now let's see. We are going to see in more details the loss functions later. I just wanted to mention them, how we can measure if a perceptron is doing well or not, or the hyperplane that it found is a good one or a bad one. Now let's see what a perceptron can do. Can a perceptron learn the data generated by AND, OR, XOR? Say, for example, the data generated by a NAND takes only 2 parameters, x1 and x2. And this is the result. So 0, 0, 0, 1, 1, 0, 1, 1. So this and this, very simple.
0.
So,
1.
so 1. So let's see if the perceptron can do this. By the way, if it is linearly separable, the perceptron can solve it. If it is not, the perceptron cannot. It can still find some compromise, but it will not find the perfect solution. I think I have a slide about this. Let's see. Yeah. So we have, this is the end, x1 and x2. So this perceptron is able to compute the XOR, the AND, sorry, with these values, -30. I don't bother, look how we found this -30 plus 20 plus 20. We don't care about this for now. We just see that it exists. Let's draw what these values are. So this is 0. This is x1. This is x2. This is 1, 1. So we have 4 points. A point here, a point here, a point here, and a point here. So 1 and 1. 0 or 1. So here we have a 1.
1.
And here, 1 and 0, or 0 and 1. This is a 0.
No.
This is a 0.
Yeah.
This is a 0. It is linearly separable or not? We can find a line that separates the ones and the zeros.
Yeah.
So something in here like this can separate them. The perceptron should be able to find this solution. We have multiple solutions here, here, here. So this is one solution. If, we, for example, we multiply this by this is x1 and x2, plus this multiplied by 20, plus this is the b. We put this here plus 1, just to, because this is the b. So what we are doing is minus 30 plus 20 multiplied by x1 plus 20 multiplied by x2. And we put it in the sigmoid. So here are the values. When we put it through the sigmoid, we get this values. And this seems like this is going to give 0 here, 0 here, 0 here, and 1 here. It seems like this perceptron is doing a good job, has learned perfectly the AND. Bear in mind that the AND is super simple. It's one of the simplest functions you can imagine. So we could find a set of weights that allowed me to use the perceptron to classify this perfectly. We learned the AND. Are you happy, guys?
Yes.
Yeah.
To make it simple with the sigmoid, when this value is below 0.5, it is a 0. If it is above 0.5, it is a 1. This is how we work with the sigmoid generally. So this value, if you compute it, you will find if the value is below 0.5, it's a 1. It's a 0, sorry. Otherwise, if it is here, it is a 1. So we just compute this, and that's it. And the perceptron algorithm is able to efficiently find these values. And by the way, when you use it, you don't need to do anything. You just supply the data set, this data set, plus the outputs, and the algorithm will find for you these values. And it will always be able to do the computation and give you the result. This is not very useful for the AND because it's so simple, but for more complex functions, it's super useful. You find the set of weights that can work with another function. And this function, we don't even know all the details about it. We just know the data set. Here in this example, we know it's an AND. But in most cases, we don't know it is an AND. We just have a data set that we got from real life, and we are trying to find the set of weights to learn the function. And by the way, once we find the weight, we don't need to learn more about the function. If it is an AND or something else, as long as we have the weight, we can compute it. Do you agree with me?
Yeah, true.
Or you're lost?
Yeah, true.
Everybody. Again, guys, always ask questions. So these are some examples. This is an AND. This is a NOR. You can see the perceptron could find the set of weights to compute the OR. The NOT is very simple. It's only one variable. This is not X and not X1. It's like not AND. They are all linearly separable. Okay? So these are fine with the perceptron. However, this is not XOR. A perceptron cannot do it, unfortunately. Not XOR is this. So let's do the XOR. This is 1, 1. The XOR is when they are different. X1 and X2 are different. It means 1. If they are the same, it's the 0.
0.
So yeah. So this 0, and so we have 4 points. We have 4 points. So 1 and 1, they are the same. It's 0. 0 and 0, it's 0. And here we have a 1, and here we have a 1. It's not linearly separable. Or is it?
Yeah.
So the perceptron can not do much. We try to find something like this, maybe this. We have one mistake here. but it's not a perfect solution. It tries to minimize the number of mistakes, so it does that, but it's not a perfect solution. However, if we combine multiple neurons, if you prefer, we can call them multiple perceptrons. These are the inputs. So how many perceptrons do we have here?
2,
2.
3,
Three.
3.
Combine them. This one is the AND, because the NOT XOR can be a combination of AND, not X1, not X2, and this, and the NOR. If we combine them, we end up with what? With a non-linear function. This is linear. This is as well linear. And this is linear.
Yeah.
One perceptron per each. But if we combine them, we can end up with non-linear functions. This perceptron of 3 neurons, not counting the inputs, is able to learn this. So the more neurons we add, the more complex things that can be learned. Okay?
Yes.
Perfect. So the goal now is to use multiple neurons and end up with multiple, like more complex functions that are nonlinear. Now let's see how the feed-forward works when we have multiple functions. So here we have multiple neurons. We have multiple neurons. These are the inputs. So what we do? So each neuron has its own weights, like independent weights, set of weights. We saw the W's for one neuron, for the perceptron, but here each neuron is going to have its own W's independently. So here it has its set of weights, 3 plus the B. Same here, 3 plus B. So we have 4 here, 4 here. It's the number of inputs plus 1. That we multiply and do the sum. We can also have the sigmoid activation here. And we have an output. And the same will be applied here. The output of these neurons will be the input to this neuron. And it will just apply the same technique for it. So here we have for 3 neurons. And for this one, A3, we just take the output and we multiply them by the weights. So these are theta or whatever we can call it, the weights or W's for here. These are the weights for this one. These are the weights for this one. And these are also the weights for this. So we multiply each output that is going to become an input by its weight. And of course, we add generally the activation function. We have multiple activation functions, not just a sigmoid. So we add the activation function to learn the class. So this is how the feed-forward works. One neuron takes inputs and produces an output. The next layer of the other neurons will take the output from the previous layer, which is this one, and compute something and has another output. We can have multiple layers. We are not like constrained to have just 2 layers. We can have multiple ones. Okay? So the input layer is called, the data are called the input layer. And each unit, a neuron, takes its input and calculated output. The activation function transforms the output to a final value. The activation function is generally something non-linear. Like I said, the sigmoid, there is a hyperbolic tangent, there are other activation functions that we are going to see along the other chapters. Well, for example, we have another architecture. You can have any number of layers and any number of inputs and any number of neurons. So here we have 3, 3, 2, 1, which means 3 inputs, then a hidden layer. This is called the hidden layer, and this is also a hidden layer. First hidden layer with 3 neurons, second hidden layer, 2 neurons, and 1 output layer. And you can see Each layer takes the inputs from the previous layer. Okay, guys? When we have here, we have seen things with only one output. But when we have multiple outputs, like here, this one, so we have our layers, and the last output will have, for example, here we are trying to recognize four classes. A pedestrian, a car, a motorcycle, or a truck. So here we will have 4 output neurons. Each neuron will try to recognize one of them. So this output means it's a pedestrian. 1 0 0 0. Same here. Here it's a car. Here it's a motorcycle, and here it's a truck. We are going to use this concept a lot when we go with the vision or NLP. So when we have like multiple classes, not just one simple binary classification, we end up with 1 output neuron per class. Also, only one hidden layer. There is a theory about it. You can find it. One hidden layer, like this one, perceptron, like this one, can approximate any function in the world. It is proven, theoretically proven. It can approximate anything, provided that we have the right number of neurons. It's hard to know it in advance. It's very hard to know it in advance. But any function in the world, any data set that has a function that has been generated by a certain function, no matter how complex it is, can be approximated with a multi-layer perceptron like this one, with one hidden layer, only one. Are you happy with this, guys?
I just have a question. How many? How can we know how many perceptron we need? For example, for the task that you show just a few seconds.
Yeah, that's a good question. There is no perfect way yet. Generally, we try to have. There are some ways you can find papers speaking about some ways, but you can find, for example, one where you always add a factor. For example, if you have some inputs here, you add a factor, the number of inputs plus like a constant, plus 100 or something. So you end up with the hidden layer that is always larger than the number of inputs. It's a good practice to have the hidden layer, what we call the hidden layer, larger than the number of inputs. But there is it's just based on experience. We will when we study more, we can find ways of, even when we go with a high number, it's not always good to go with a high number because of overfitting. We can find there are ways that can work very well, but we are going to try them later.
You mean that the number of perceptron in the hidden layer depend on the number of entries?
Not just that, the number of entries and how complex your function is. Because the more neurons you have, the more complex, the more expressive your neural network can be. For example, a very complex function will need more neurons, of course. We don't know what they are doing, but the more complex it is, the more neuron it is. So it doesn't only depend on the number of entries.
But suppose we have a million of image that we will use for training. It doesn't mean that we need a million of perceptron.
This is not the number of. This is not the inputs. A million is the number of examples.
Yeah.
The number of
suppose
inputs
we have
are
a million
the
of
pixels.
examples.
Yeah, the number of inputs are the pixels or some features that we compute. So it doesn't really depend only on that, on the number of images you have. It's how complex it is. For example, objects in images tend to be a bit more complex. Or let's say to recognize a face, for example. It's something that can be complex. So we probably need a lot of neurons. This discipline is a trial and error discipline. So you have first to try with a certain number of neurons and see. Generally, always go with a number of neurons that is higher than the number of inputs. And it's really instinct-based. You can feel if your function that you are trying to approximate, you can feel its complexity. And then adjust the number of neurons based on how complex it is.
Okay.
Okay, and it is really experience-based. There is like no clear way to find the best ways.
So for image, generally, it depends on the number of pixels in the image.
If your pixels are features, but it's not necessarily that case. You can use something else, not pixels as features. You can pre-compute something and then use that as your features, and you can reduce your dimensionality. Okay. It's when we reach that part, we are going to do these things.
Okay.
Because the features are and the strength of deep learning actually is that we are able to compute features on the fly. But for now, let's focus only on this part. Guys, someone is using a microphone, so please. Can you mute yourself, please? Thank you. For this discipline, guys, you really need just experience and to try a lot to understand these concepts. Because I know right now it looks very like fuzzy, these explanations. But once we practice on real cases in vision and NLP, things will become clearer. And this number of neurons things will not become like a very big issue. We'll still need like to do some trial and error, but it's not like a huge issue in many cases. Now let's go to the loss functions. So how can we find the best parameters? W's. The neural network by itself, of course, does not have a mechanism to find them. So let's take that just the case of the perceptron. This is the perceptron. It has W1, W2, W3, and the B, what is the bias? X1, X2, X3. So our goal is what? Guys, our goal is what? What
to
do
find
we want?
The best parameters? We need to find the best.
Exactly. Our goal is to find this, and this. All the rest are known. The X1, X2, X3 are coming from the dataset. We know them. Here we have the sigmoid of the input, of the output, sorry. So what we don't know are the W's, W1, W2, W3, and B. So our goal is to find them. This function by itself, sum xi wi plus b. So this is for one neuron, just to make it simple. So this function by itself, like when we see some W's, we can't know if in advance some W's and B, a formula like this, we can't know if they are good or bad just by looking at them. What shall we do to know if they are good or bad?
We test them against the dataset?
Exactly, yeah. We test them simply against the dataset. So we have here the input and here the output. So we want them to predict everything right on the dataset. When we use this input, here, we take the x's, put them in here. We want to find the right y. And for all samples. Yes or no? We want to do it for all, but this function, this perceptron will be right for all samples. It's going to predict, let's say 0, 1. It's going to predict if it is a 0 or 1 for every sample, correctly. Ideally, that's what we want. How can we do this? How, like a very naive approach would be to try randomly. Try some W's and B, test them and see which one is the best. We can do that. We can do something like that. Try some random values and see and check. We can do that. But this is not a very clever approach. It's not a very clever approach to do that. We can spend 1 year doing this, especially if the problem is very complex. So what we use the loss function. The loss function that is able to measure the performance of this against this. It's something close to what we just described. And we have a number of loss functions. We have the mean square error, the mean absolute error. These are very simple errors. And the cross entropy. These are used mainly for regression when we want to predict a number in a continuous value. And this is used for classification when we want to find a class. Do you want, Guy, a pause at this point? What do you think? Do you want a pause or shall we continue?
Yes, maybe 10 minutes.
Sure, yeah, no problem. Okay, let's have a 10 minutes pause and we continue.
Okay.
This conference will now be recorded.
So let's go back to our loss functions. So this loss function is some measure that tell us about the performance of our model, of, in this case, the weights that we have found. We have the mean square error that are used for regression, mean square error and mean absolute error, and the cross entropy, the famous cross entropy. It is used in logistic regression and quite a lot in deep learning. So why do we use such functions, and why do, in your opinion, why we just don't use these functions, for example, this one, and we don't just count the number of good examples or bad examples, and we try to optimize them? Why do you think that we need to do something like that? We can count here. We have one bad example, and we can say that this is 1. The higher it is, the worse. So we want this function to be 0. We want it to be 0. So this is called the 1-0 loss. It just counts the number of misclassified examples, like in here, this one. So why don't we use this kind of loss functions? Can you tell me why, guys?
Because we need to know how much the error is and apply backpropagation, no?
Well, backpropagation is just a trick to accelerate the computation, to accelerate the derivative computation. But why, like, we don't just count the number of misclassified here? We have 1. If it is like this, it is a 0. We don't have any. So why don't we just use this case?
For accuracy?
Accuracy of what?
The outputs against the dataset.
Yeah, but this one will tell you that you have 1 error.
But it doesn't. What it help us to know which weight we should change.
That's it. Yes, we need to know how we should change it, because if it tells us we have only 1 error here, and here it tells us 0 error or 2 errors, we won't know how this should change. My weights, WI, we don't know how to change them. It just tells us we have 1 error. So what shall we do? Rotate this direction or rotate to this direction? You can rotate it like this or rotate like this. So it doesn't really tell us how it should change. So we need something that can tell us this, gives us this information. Do you agree with me, guys? Yusuf, do you agree?
Yes, yes, yeah, I got it.
It's better if it tells us, if it can tell us how we should change. It's better than if it tells us only how many good or bad examples we have. So we want something like this, something that is derivable and preferably convex. You know what is convex?
Have a minimum, have a local minimum.
Only one minima, one global minimum. So what we want to do, what we want to do, let's take this loss function. It computes, like it gives me a value, like a good value if everything is right, a bad value if everything is not right. The classification is bad. This is what it does basically. So we want this. If it is a high value, it's not good because it's called a loss, how many losses we have. If it is a low value, it's good. So what do we want this function to be? How do we want it to be? Ideally, what value it should take? Ideally. What value it should take ideally?
1.
Can you just repeat?
So this loss function, how do we want it to be? It computes if it is
0.
We want it, yeah, we want it to be 0, ideally, because it computes if it gives like a high number if we have a lot of errors, a low number if we have less errors. So we want it to be 0. If it is 0, it means we have no error. Actually, there is more to it than that. But we are going to see these stuffs. It's not just the number of errors, etc. So it tells us how many errors we have. If it is a high value, it's not good. If it is a low value, it's good. So it is 0, ideally. Do you agree with me, guys? You lack energy today, guys.
But we still don't know how this influence any way and which way.
I couldn't hear you.
I said even if we know the result of this function, we still didn't know how which weight we should change.
Not yet, not yet.
Yeah.
We are coming to it.
Okay.
But we want this function to be 0. And if we can't, we want it as small as possible. Yes? Do you agree?
Yeah. Yeah.
So we want it as small as possible. This is the goal. W's multiplied by x's plus b, we don't know how they look like. What's the ideal one? We will never be able to know just by looking at it. It's just a number. But if we plug it in here, this is the function that the neural network is trying to learn. This is just to simplify. It's not necessarily this. This is only from one neuron. When we have like multiple neurons, it's different. It's more complex than this. So this one, sigmoid of this, actually, what does this? Is the y that we are going to compute, and also the y that is here. Sorry, it's this y hat. The y is not computed. The y comes from the data set. This y comes from the data set. And this one is the computed one by my neural network.
Predicted.
Predicted one, yeah, by this. If we are using just a perceptron. So this can be replaced by this formula here. And if we are trying to minimize this, to make it as small as possible, we are trying to find what are my variables here. This is
Global global minimum?
What are what are the variables and the constants here? Is n a variable or a constant? N is the number of samples in the data set. Yes. N is the number of samples in the data set. It is constant. The data set doesn't change. This is n. How many samples do we have? The yn is constant or a variable?
Constant.
Constant as well.
Constant. It comes from here. And this one comes from here. This is the sigma.
It's available.
Yeah. So what variables do we have in this formula? What are the variables?
The W.
Y hat.
Y hat is this.
Computed Y hat.
Yes, it's this formula. So my variables are Wi and B. X is variable or a constant?
Constant.
Comes from here, from the data set.
Yeah.
So my only variables are my W's, because this one is this. And this is just for the sake of simplicity. We're using only the example with one perceptron. So we are trying to find the W's and B that will minimize this. So we know now, what W's to choose. We need the W's that minimize this. If we didn't use this, we have no idea how to find these W's, because just looking by eyes doesn't tell us if it is good or not. But this one can give us a measure if my W's are good or bad. Then what do we do? What shall we do now? It's now a classical minimization problem. Is this derivable? Is this function derivable? This is just a multiplication of variables, this one. All the rest are constants. It's just a multiplication of some variables.
We try to derive it and...
Is it derivable? Do you think this one is derivable?
The constant go to 0.
But is it? No, I'm not computing the derivative yet. The partial derivatives, I'm not computing them. Is it derivable? Can we derive this?
Yes, the polynomial.
Yes.
It's a polynomial in a log. Well, it's derivable in a certain interval, because here it shouldn't be negative. But this one should not be negative, because why? We are predicting 0 or 1. It should be something close to 0 or 1. We can make sure that this one is between 0 and 1. So this one is going to be derivable in a certain interval. It's derivable. Now, if you try to remember some calculus courses that you had before, how do we compute the minimum of a function? How do we compute the minimum of a function?
We derive the function and then put it equal to 0.
Perfect. Yeah. It's just the derivative of my function I equals to 0. So if we find the solution, the set here, it's W's. The variables are W's. Wi. If we find, we derivate this, and we try to solve this equation. We find my W's, and it's done. We found the minimum. But in our case, I will express the convexity later. So we want to minimize the loss function. And by this, we should find the derivative equals 0. But sometimes it's not that easy to solve this equation. Analytically, I mean, sometimes it's not that easy to find what's the W's that can make the derivative equal 0. It's not that easy. So what we do, we use the gradient descent algorithm. we use the gradient descent. Most of you have heard of it. It's like whenever you have neural networks or any other things, we have this algorithm popping around, the gradient descent. Let's see how this gradient descent works. I have a problem with this video. It's just an image for, I think I made a mistake copying and pasting it. Let's see, I feel I have it here. My previous slides. Here it says a problem. Okay. Let's try to find it here. To find this illustration, it's quite cool to see it. Yeah, this is the one. So let's see how it works, this gradient flow. So you saw how it works. Let's go back to our slides. So this is, we want to minimize, for example, this function. This is my loss function, cross entropy or whatever we are using. And we want to minimize it. Here, how many features do we have? So this is the error here to compute. And how many features do we have?
Just one.
2 features. We are in 3D. So this is the error height, how many errors we have made, the error value. And we have 2 features. We have one W and one B. It's just one thing, WX plus B. And this is the error. So the error is here at its highest. It means that this W, this is the B, this is the error level. And when we project this in here, also this value, this means that this W and this B are quite bad because they go here. The error is very high here. Or I don't know what W it is, probably this one. Or it means it's very bad. The error is very high here. And the best value is here. B of this value and W of this value, because it makes the error almost like 0. Can you see this? Can you see this, guys? Do you agree with me?
Please repeat this, Rida.
Yeah.
So we know that The top is like the highest error.
Error, yeah, we are computing the error according to W and B. These are our only variables.
Yes.
So this is the error, and this is W, the W and B. So this point here is bad. The error is very high, as you can see.
True, yeah.
But this point is good for this W and this B. The error is very low. So we take these values as our best W and B. But to find them graphically, it's very easy to see them. But if we can't draw them graphically, especially when we are in a high dimension, we use the gradient descent. Like we said, if you remember in probably high school, we use this algorithm. We knew that if we can't, for example, find this solution, if we can't, it's very hard to solve. It's a function that is hard to solve. What did we do? We did something like this.
Changement of variable?
No, it's not that. It's even simpler than this. Do you remember this? What does it mean?
Okay. If we have interval, there is a solution.
Exactly.
Yeah.
Exactly. If we have at least one solution.
And it should be the multiplication inferior to 0.
Yes, if the product of these two is less than 0, is negative, it means in this interval at least we have one solution. You remember we used something like that when things are very complex to solve. We can't solve the equation, so we try to find A and B numerically. We try to find the smallest.
Approximation methods or something like that.
Yes, it's an approximation. But in the gradient descent, maybe the solution doesn't even exist. It cannot be 0. It's also possible. So we're trying to find the minimum. Try to find the minimum. If it is 0, perfect. If it is not, we try to find the minimum possible value. So what do? We go somewhere. Let's go to the next slide. It's probably easier. Or I will draw something in 2 dimensions. Let's say we have only this. This is my loss function. Can be called J as well. And we have only one variable, 1W. We don't have a B for the sake of simplicity. And this is the loss. Does this loss function equal to 0 at some point? Does it equal to 0?
No.
Never. So this doesn't exist. This will never be 0. The loss function. Then we try, like with the derivative, equal 0. Equal 0. Now we try with the derivative equal 0. We try to find this value. Of course, we cannot find it analytically. It's difficult to solve this equation. So what do? We use this gradient descent. We take any point in here. For example, this one. When we compute the derivative of L in this point, let's call this point C. L of C equals some value. Let's say it's a 10. That's the value. And this, the derivative of L for C. What does it represent graphically? What does it represent?
The tangent, or
exactly, yes, the tangent, the gradient, which is the tangent, this slope. It represents this slope. When this slope is horizontal,
It's 0.
When this, exactly, it's 0. When it is horizontal, it is 0. When it is vertical,
Positive.
well, this is negative. Well, we don't care about the vertical one. This is negative, and it is steep, and this is positive. Which means that when the slope is that way, is pointing towards this direction, what does it mean? That there is a minimum into that direction. There is a better value than this in that direction. Can you see this? It's clear. When the slope points to this direction, which is a derivative actually, by the value of the derivative, when it points to this direction, what does it mean? For example, when you are in a mountain and you are here, and you feel like there is more to go here, you know that there is a lower value than where you are. You can know it because where you are sitting has like this kind of slope, a slope pointing toward this direction. You can feel the slope. The slope is the derivative of the point where you are. So when we are here, we compute the derivative and we found it negative. What does it mean? We should go into this direction to find a better value. If we go this way, we will find a lower error. So we keep going. Let's say we jump here. We compute the slope again. Is it negative or positive?
Negative.
Negative again. So we should continue. We should continue until we reach this point. When it is 0, what does it mean? The slope is 0. We are at the bottom.
At the bottom.
We are at the bottom. It could be the opposite as well, guys. It could be the top. The slope is also 0 here. But we will never go to the top because we are going to the direction of the slope. Because the gradient here is positive. So we go towards the negative value, towards the negative gradient. So this one is negative. We keep going here until we reach. But sometimes, because we don't jump by small values, we jump by some values. We go here, then here, for example, then here, then maybe we jump here. Here the gradient is what? Is positive or negative? The gradient here is positive or negative, guys?
Positive.
Positive.
Yeah, it's pointing towards the top. It is positive, which means we have to go back. It means we have jumped over the minimum. So we go back, we go to the other direction, but with a small value. So we won't oscillate. And we go, for example, here. We find the gradient equals 0 or very close to 0, because numerically we rarely find the exact value. Once we come here, this is my minimum. We take this W, we compute the loss. It's very small, almost 0, and we use this W in my function. We don't have a B in this case, but if we had a B, we put it. If we have multiple W's, Wi, and then now we have our perceptron by this gradient descent. There are multiple algorithms to find these W's, but the gradient descent is one of the one used most in deep learning, in neural network and deep learning. There are methods that use a second derivative, etc., but they are very computational heavy. So we use a lot this gradient descent. Do you understand how we are finding now the W's? My weights or my coefficients. Is it clear for you? We have an error that we want to minimize. The error is derivable, continuous. We use it to find its minimum. The W's that gives us the minimum for this loss function are the best W's, more or less, of my neural network. We plug them in my neural network, and I have my solution. Are you happy with this explanation, guys?
Yes, Reda, just I have a question. we calculate this loss function for each neuron of my model.
No. It's a one loss function at the end. The loss, because for each neuron we can't know. We don't know how the output should be. We know the output of the end, because this function is computing the error based on the last output. It's comparing what we should have from the data set against what the whole neural network computed. If my whole neural network is just one single neuron, then we use the output of that single neuron. But if it is more complex, we use the output of the last layer. Okay? We need the final value. We can't measure, for example, these values. We cannot measure if they are right or wrong, because we don't know how they should be. But we know how this should be from the data set. We know what value we should have here, because this is the final prediction.
Yes.
So
but I can't come back after when I have corrected the white. It's okay. It's just for keeping the white, the correct white. That's all.
Well, the correct weight will give you the best output. Will give you the right output. We are going to find all the weights. Gradient descent will not find only the weight for this or this or this, because it's trying. It has the whole function for this whole combination, and it's trying to find all the weights together. Okay.
Maybe,
so I trained just for one time. I learned this one time.
What do you mean by one time?
I mean, if I find the output, it's okay. So I learn. I pass all this layer.
Of
and
course,
then
the output, to find the output, you have to do all the operation across all the layers.
Yes. So, and then I get the best white after with calculating the loss function.
If you optimize the loss function, if the loss function is at its minimum, you get the best combination of y's. You have multiple y's because the dataset contains many y's. So you get, in average, the best combination of y's, the correct y's to the maximum.
Okay. Then after, it's okay.
You have your weight. That's all. You have now. You need your network to make predictions for the values that are going to come in the future.
But Reda, excuse me.
This is training. This is training. Okay. So I have get the best.
Training is done once you find the y's, the different y's, the weights. Training is done.
Okay. Okay.
The goal of the training is to find the y's and the b's. We have the y's and one b per each. And later, once you have them, you can use them for prediction.
Okay. Now it's clear. Okay, thanks, Reda.
Excuse me, Reda. The loss function allow us to calculate the good W's or
W's, yeah.
The previous layer, just the previous layer, no?
No, everything. The loss function helps you to find the W's for all the weights. When we get to back propagation, we are going to see how it does it, but not just the previous layer. Everything.
But show us the slide of the loss function, please. Yeah, here. I thought that we have just the previous layer. We have all the layers.
No, we have all the layers. I did the example with one single neuron just for the sake of simplicity. One single neuron is Wi, Xi plus B. But when we have more, it's more complex than this. You have to replace all the X's by other stuffs. Here is a sigmoid of this. When we have multiple layers, these X's will be inputs or outputs of the previous layers. So this function is going to be more complex. This
we
is
do
the whole neural network representation.
So we do the calculate the minimum for all the layers at once.
The loss function computes the minimum for the output of the network. The output of the network is a combination of all the layers. It's computed based on all the layers.
Okay.
So here we have all in this equation we have all the weights for all the layers, not just the weights of the first layer.
And the is different for each perceptron, or it's the same for all?
Sorry, what?
The B.
No, for each neuron has its own B.
Okay.
Yeah, each neuron has its own B and its own weights.
Okay.
We are going to dive deeply in this concept, especially with backpropagation. And by the way, backpropagation is, we are not obliged to use it. It's just a trick to make the computation fast. That's all what is about backpropagation. The mathematical foundation is what we discussed today. We have a number of weights, the W's, that we are trying to find that will minimize my loss function. It's exactly how you used to do in high school, how to compute your derivatives, etc. Okay?
Okay.
Now, another problem. We are almost done for today, guys. Another problem.
Sorry, Rida. And what about B? It's like now the gradient descent or loss function help us to calculate only W.
No, WB is
so W and B, okay.
It's
so
because fx, a linear function is fx equal or it's always ax plus b.
Okay, got it.
So we always need this value.
Okay, thank you.
Okay, now one of the problems with the convexity and non-convexity is that my loss function can have a shape like this. The gradient descent will follow the slope. It's like you leave a ball at the top of a mountain and it will roll in a certain direction. So if you leave the ball here, it can end up here, which is probably the global minimum. But if you leave it here, it can end up here, which is not the global minimum. It's a good minimum, but it's not the global one. It's a local minimum. You can see it. Can you see it, guys?
Yeah, it's clear.
Yeah. So the final solution with the gradient descent is always dependent on the starting point, where you are going to start. And you will never know what is the best starting point. So a good thing is if you are able to have a loss function that is like this. This is what we call a convex loss function. It has just one minimum. In this case, the gradient descent will guarantee to converge to this local minimum or global minimum, sorry, because we have only one. If you follow the slope, we end up in the minimum. We have only one. When we have one single neuron, the cross entropy is convex. When we have, even for this or this, when we are dealing with regression, these functions are convex with one single neuron, which means we will always find the best set of weight that will minimize my loss function. But when we are dealing with deep learning problems with multiple neurons, this no longer holds. We will end up with things that complex. And the solution, like we will never guarantee to land on the best set of weights. If, for example, we start here, we might end up here, which is a best solution. This one and this one looks the best one. This one looks good enough. This one looks bad. So when we have multiple minima, we will not guarantee the best solution. And this is a problem that hasn't been solved even today. But it works. Even that way, it works. We are going to see why later. There are multiple things to consider to know why, and we are going to dive deeper in multiple scenarios why this works, and the different variants of gradient descent. We don't have only one variant. We are going to see the famous one like Adam, RMS prop, or the SGD, stochastic gradient descent, which is the original one that was used before. We're going to see all of these concepts. I think we should stop now. That was a bit intense. What do you think, guys?
It's fine.
Yes, it's fine.
Fine. You mean you want to continue, or it's good to stop?
For me, it's good to stop. It was a lot of information.
Yes,
Yeah.
yes. We probably need to revisit these aspects later again. I know it's not trivial to understand.
It's very new concept. Yeah.
Yeah. No problem. We will revisit them. And there are, but if you've understood like 50%, so I will stop the recording now. Stop. So
Reda,